Hello everyone, welcome to another week of N3AS seminar. Today we are really glad to have Bhaskar Dutta from Texas A&M University to give us the today's seminar, and he's going to tell us about light dark sector inelastic exploration. So Bhaskar, you may start.
Thank you, Mrinal, for inviting me to speak at this venue. And as Mrinal said, my title of my talk is Light Dark Sector Inelastic Exploration. So the way I would talk about this topic would be as follows. First, I would discuss like a couple of model scenarios where light dark sector is possible, and basically what we'll be doing will be trying to get a light mediator and sub-GeV dark matter, and then using these models, the strategy is to search for this light dark matter, and I would use beam dump based neutrino experiments, and then also light dark matter which is around us, and I would use the large neutrino detectors. And now, of course, there are many papers on these topics. One particular line of exploration I would use would be this nuclear inelastic. And at the end, you'll see some de-excitation line, which I would use. And, you'd see that these de-excitation lines would provide a kind of the base sensitivity at this point for most of the parameter space what we'll be describing today. And then I'd conclude. And so why is this light scale? But these scales can be anywhere. And, there are some tension in terms of these origin of dark matter, neutrino masses mixings, and there are various anomalies. And LHC is probing these scales above 1 GeV with a high sensitivity. And so what we'll do, we'll use this sub-GeV scale using these direct detection experiments and the beam dump experiments. And so sub-GeV scales can be as good as these scales above GeV, and they can also explain all the anomalies puzzles. They can explain the dark matter content of the universe, and also the neutrino masses mixings and everything, and all the anomalies also can be explained. And there are lots of ongoing activities, and in terms of this light mediators, which could be scalar, pseudoscalar, vector, and this sub-GeV dark matter. And so, there are many directions one can use these models. For example, gravitational wave or primordial black hole formation and all this stuff. But here, just I would use the light dark matter part of these models to explore. And so one such extension could be just a U1 T3R. So here this additional U1 group anomaly free, which is introduced where the right-handed fields of standard model have charges. And but this U1 T3R does not contribute to the electric charge, and this symmetries were spontaneously broken by some Higgs mechanism at around 1 to 10 GeV scale. And also we have this eta L and eta R, which would contribute to this dark matter candidate of this for this model. And then this phi is the scalar field which develops this fib to break this symmetry U1 T3R. And at the end, there would be a remnant Z2 symmetry. But this is, again, as I said, this T3R does not contribute to the electric charge. And why this model is introduced, it addresses the U-core coupling hierarchies in standard model, because we see a huge hierarchy in terms of this coupling, like 10 to the minus 6 to all the way to 1 top quark coupling, electron coupling. But here, in this case, when phi couples to the right-handed field, then this U-core coupling for the first two generations, for where we are introducing this symmetry, then it involves this non-renormalizable looking operator, which is H and phi, is made out of the standard model Higgs field and this phi additional field which we have introduced. And then the net effect is to produce all the masses. So you don't really put any coupling by hand to be 10 to the minus 6. Here the couplings could be order 1. And of course, this operator looks, as I said, is a non-renormalizable term, this term in the Lagrangian, but it can arise from this renormalizable Lagrangian at some high scale, and where you can introduce this vector like fermions, and when you integrate out, then you get this term, the Lagrangian. And this, again, you maintain the symmetry in this when you write down the full Lagrangian, which is renormalizable. And, the details are provided in this paper. So if one wants to see how these terms can be generated from a renormalizable Lagrangian. And but at the end of the day, we have standard model Higgs field, as well as this phi field, and this phi scale of phi is about 1 to 10 GeV to break the symmetry. And now, once you set this symmetry breaking scale and this mechanism to produce the masses, and then you more or less fix all the couplings. So, for example, this new scalar couples to the leptonic fields with the mass of the lepton divided by the new vacuum expectation value, and similarly, the other all other fields gets get to couple to this new scalar by this fixed coupling. And then this eta 1 and eta 2, they arise from the combination of those eta L and eta R. And they also have couplings to these phi fields. And you can see this is the flavor conserving piece with the tops to this scalar one. But also you have this gauge part. And when you expand it, and again, you'll see that the gauge coupling to this scalar is also fixed by the gauge boson mass divided by the V, and also this etas start talking to this A field, and here the coupling is Flavor non-diagonal by construction. Now one can look at the parameter space. So for example, here we are looking at the parameter space where the symmetry works between the first generation quarks and the second generation leptons. So similarly, one can have an electron model or combining both generations. So for this one, the parameter space could be like this, and also G-2 gets contribution both from phi prime and A prime, and at the end one can show that the G-2 excess can be explained in this context. But the dark matter side is an interesting story, because now we have both A prime and phi prime mediation going on for this dark matter is made out of etas and the eta annihilation. And this one would be S wave and this one is P wave. So if really one needs to satisfy the CMB constraint, one can have some more of this phi prime contribution. And so, it's easier to satisfy the dark matter content in this kind of a model where this additional scalar is present, in addition to the gauge boson. So one can also extend all the other similar types of activities for L mu minus L tau, U1B, U1L, U1B minus L. They are just, in addition to this, just the gauge boson, you introduce this scalar or Higgs effect to break the symmetries, and then right away you start to generate this kind of light, expanded light dark sector, which has interesting contribution to the to this dark matter sector of the physics. So now this just I mentioned extending the standard model gauge group, but in addition, one can also add the expand the Higgs sector of the standard model. Just we have a one Higgs doublet, but one can add multi-Higgs story to it, like for example, two doublet or triplet or a singlet. So any kind of combination one can add to expand the Higgs sector. And the idea is then one would minimize the Higgs potential using this expanded Higgs sector, and then try to figure out what's the Higgs mass spectrum. And in that way, actually, we did that analysis, and using one singlet extension, like a two doublet, one singlet, or two doublet, one triplet, one singlet, various extension. And in all these possibilities, we found that it's possible to generate a light scalar with a mass, sub-GeV mass. And these models are also interesting because one can have an NSI type of terms, like a neutrino interacting with this light scalar, or neutrino interacting with any of the Higgs scalars, so light scalar. So that light mediator probe also can look for these NSI terms in various neutrino experiments. Also, not only this are like a neutrinos which have weak interactions, so one can also introduce new type of neutrinos, or heavy neutrinos, or sterile neutrinos in this model, and with a coupling N and phi. And this sterile neutrino structure also can be used to explain mini Boone anomaly, or also it can be a dark matter candidate. So the bottom line is, even if you do this, instead of going for the gauge extension, one can do the Higgs extension. And even in that case, one can generate this light mediator, and with a possible dark matter candidate. So that, of course, these models are different in terms of the predictions. For like a first one is this gauge boson. Also, it has various standard model couplings and their decay modes and all this stuff. And the second model also has this light scalars, so pseudo scalars. Actually, one can have both light scalars and light pseudo scalar in the second version. Like various possibilities are there, and also in both cases one can have dark matter candidate. And as I said, this model has this symmetry, dark sector symmetry breaking, have a scale or dark matter, dark sector symmetry breaking scenario, where also one can try to understand whether there is a strong first order space transition is ongoing, and then try to kind of discriminate these models based on these gravitational wave signals, or subsequent PBH formation and all this stuff. But we are not getting into those. Some of these works are in progress right now. But what I will do, I will explore just the light dark matter of these models, emerging from these models at neutrino experiments. And for example, I use that like a beam dump based experiment. For example, coherent CCM, JSNS. 2 CCM is the coherent Captain Mills, and this is J Park SNS sterile neutrino search program. And actually, these experiments, why I'm mentioning these, because these experiments put the best constraint in the light dark matter parameter space, most of the light dark matter parameter space, based on this elastic nuclear scattering. But what I will do, will use the inelastic scattering, and to show like what benefit do we get using those line signals. And similarly, the ambient dark matter, but in that case, we'll use like bigger detectors, large scale detectors like a Juno, Boex, Dune, and Hyper-K to probe that parameter space. So just to start with the neutrino experiment, short baseline neutrino experiments, there are many of them, or many are ongoing. Like a proton beam, like a 800 MeV to 3 GeV, these are ongoing. And then of course, Fermilab SBN program is also ongoing at GeV, and then also NUMI beam with 120 GeV. And so, all various facilities. So it gives us an opportunity to produce the dark matter, this light dark matter in the lab, and then to detect them in some neutrino detectors. So what happens in this experiment, proton hits some target or dump, and produce many of these particles like photons, electrons, pions, kaons, etas, and all this stuff. And all these particles can produce then our light mediators, which are made out of scalars, pseudoscalars, or vector bosons. So various possible ways you can create those light mediators. For example, photon converting into A prime. For the if you have this scalar or pseudoscalar mediator, then you use the Primakov to produce them. That means there are lots of photons. The photons hit this target, and this high intensity photon factory, and so then you can produce them. And then also from E plus E minus, so Compton, associated, resonance, Brem. So there are various ways you can produce all these light mediators in these facilities. And also then the pions, usually we always use the pions or kaons to produce the neutrinos. These are neutrino factories, but these pions, kaons also can produce these light mediators via three-body decays. And three-body decays are also interesting in these cases because they are not helicity suppressed. So you actually focus the pion kaon to get more enhanced neutrino beam, but also in that process you are enhancing this three-body decay mode outputs. And so there could be a large intensity of these light mediators coming from those decay modes as well. Oh, and of course, the most familiar one are like a eta 0 pi 0, which decays into a photon and a prime, so neutral in some cases. And so people have used these modes for various physics purposes, dark matter, and then also explaining the mini-moon anomalies and all this stuff. So, but again, as I said, I won't get into those. I'll get into the light dark matter such. Of course, proton Bremsstrahlung is there, and then parton interaction, Rayleigh process. Those also could help you to produce these things. And so I'm just going through these things because not only A prime, but you also have all these mechanisms to produce these scalars and pseudoscalars, which can also decay to dark matter, light dark matter final states. Also, there could be nuclear de-excitation lines which are available in those targets, and then those also can be converted into scalars of these various mediators. In addition, all these facilities have tremendous neutron problem, and one can convert those neutrons also to some signals because by using the Bremsstrahlungs or neutrons on target to produce some light mediators. And we have done some work in that direction for phasor, but those can be done also for all these facilities. So there are many ways the light dark matter, if there is a model which has a light mediator like a scalar, pseudoscalar, or vector, it seems that there could be many, quite a few possibilities to produce them at these beam dump facilities. And then the next step is dark matter then decays into, mediator decays into dark matter, and then dark matter appears in this detector and produce some recoil, and then that's the way all the bounds are set. And so this is the elastic scattering channel. And so here I'm using this vector mediator, but one could have used a scalar mediator or pseudoscalar or whatever you want, because those are also possibilities here. And so I get into this 1 GeV based coherent type of experiments and coherent scattering based experiment, which happened in this coherent experiment at Oak Ridge, or CCM, also JSM square. And here actually proton hits the target, and then you produce pions, which are charged pions, which are stopped, and pi minus gets absorbed, and charged pion is stopped by this electrical environment of this target. And then pion decays into muon and nu mu. Here, the nu mu comes with a 30 MeV. So this is the prompt, and it's like a 10 nanoseconds of that order. And then muon is a decay, which is a delayed, it's about 2.2 microsecond, and it produces also these neutrinos. So then this distribution gives you those delayed distribution. And this experiment not only measures this energy spectrum, but also the timing spectrum. So timing spectra actually gives you this prompt neutrino evidence, and the delayed gives you this nu bar and nu e. And so they use a pulse beam, and then using these neutrinos, this coherent scattering has been established at 11.6 sigma, by their cesium iodide data. Also, liquid argon is also giving this 3.8 sigma excess, which can be explained by coherent scattering. So now this is a neutrino experiment, and if you want to search for dark matter, you right away face this neutrino background. The question is, how do you remove it? So, but since these experiments use timing and energy measurements, so what one does use the prompt window, and that's the place where the pion decays promptly to muon and nu mu. Actually, in the prompt window, also the dark matter shows up, because pi naught decays with a kind of a very small lifetime. So that's why the prompt window is kind of needed for us for the dark matter study. And then but then there also appears this nu mu's, but nu mu's, as we have seen, it mostly appears with the 30 MeV. So there is a maximum energy recoil. And so if you require this like a time to be less than 1.5 microsecond, you can see this microsecond is of the order of muon lifetime. So that's the scale here. And if your recoil is greater than 14 keV or so you can beat the prompt, you can kill all the neutrino background. So that way one can really, not all, but most of the neutrino background, you can make this region kind of ready for dark matter probes. And of course, this is not the only way. There is another way, is by looking at the delayed neutrino spectra, you try to guess what could be the prompt neutrino, and that's the way one can remove the neutrino background. And so for this first technique, where you apply the timing and energy cut, for that you need the initial time, that means when proton hits the target. And the second one, you don't need that, but second one also can have a non-standard neutrino interaction background. The first method is being utilized by CCM. The second one is being utilized by coherent. CCM has a good measurement of T0, so that's why they could go for that. So, if there is a signal, I think both these would help us to establish a signal. So that's what this this is the nuclear elastic scattering, coherent elastic scattering. And so the parameter space, you can see that this is the coherent constraint, and this is the CCM. CCM constraint is far above because it's from their engineering run. Their current run has more POT, and also 7 ton, and and with a much better background reduction. But anyway, the coherent constraint is here at this point, and this is here, and this little extension is produced from NS64. But if you really look for these hydrophilic cases, then NS64 does not produce any constraints. So for example, E1b, there, of course, this constraint is purely from coherent, and then this is the CCM. This is the elastic dark matter scenario. So now what I'll do, I'll try to use this the nuclear inelastic channel, and which produces a line signal, because A prime produces this N star excited state, and then N star produces this N and gamma, and then it produces this MEV level signal. And so once you get into the inelastic calculation, of course, your cross section becomes much more elaborate. So you can see that these multiple operators start showing up. But and also the calculation is like a time consuming and lots of you need high scale computation. And but one interesting thing is in the large wavelength limit, this cross section actually reduces to this Gamow-Taylor Gamow-Taylor part, and actually the Gamow-Taylor actually dominates the cross section there. And in fact, what we have found that also if for this recoil like which can be produced here, for that Gamow-Taylor more or less gives you the right magnitude of the cross section. So what we did, we used about 100 excited states, but also kept all the Gamow-Taylor contributions. And then we found that the Gamow-Taylor contributions more or less saturate this all the excited states what can contribute to this cross section. And so we use this big stick for our nuclear cross section calculation. And so now at the upfront, the inelastic to elastic cross section is like a smaller, like a 1 to 3 order of magnitude smaller. But interestingly, why inelastic still can give you a better parameter space, because here it's a line signal. So you have a much less background to confront with. And also, this is a MEV region. Here, the neutrinos, what you have seen so far, is producing most of the backgrounds in the KEV region. And for MEV region, actually, is background is much, much smaller coming from the neutrinos. And so now the for argon, so what we'll do, we'll use this line strategy for the coherent Carmen, CCM, and the one future PIP2BD, which is the formula-based proposed experiment, and they use 100-ton liquid argon. And so this argon line appears between 9 to 12 MeV. And so, but the carbon line, for example, which comes in the case of Carmen is done. Carmen has taken data till 2000, and they actually measured this 15.5 MeV line based on the neutral current. It's also a 800 MeV beam. It's a nu mu from the nu mu scattering. They saw this like a neutral current based excitation or de-excitation photons. And so one can utilize that to obtain constraint in the existing parameter space. So for example, this is the Carmen line, or the excitation events, de-excitation events associated with the 15.5 MeV line. And CCM 120, this is the like a experiment engineering run data. So they are not yet sensitive to the argon line, but in CS 200, the CCM 200, this background would be reduced by 2 order of magnitudes with shielding and few other techniques. And so they should be able to see that that inelastic neutral current argon excitation line. And CCM or coherent is their cesium iodide data. They are not sensitive to any MEV region physics, but their sodium iodide ongoing run would be sensitive to. And so now, based on this inelastic calculation, we can see that this is the existing elastic constraint, but based on this Carmen, which already beats all this elastic constraint, or including the NS64, which comes from the electron beam down. And here, for example, fermionic type of dark matter, this is the scalar dark matter. And so PIP2BD, which is 100-ton, and also CCM is planning to use an 100-ton in the near future. And you can see that you can prove this thermal relic line for the pure like a hadronic channel. And so now for carbon, one can use the experimental line to kind of calibrate big stick. And also for argon, we use this experimental paper to calibrate our shell model calculations to make sure that it takes, it gives us the right prediction for this inelastic cross section. So now, if one take it for the pure hadronic case, one can find that, of course, you don't see the NS64, so the bounds become a lot more clearer in this game. So you can see already the Carmen is beyond everyone, and these are kind of ongoing coherent and CCM, and this is the 100 ton. So 100 ton, of course, would be much better, but this is the sensitivity one can get. So now one can also apply this to the ambient dark matter, but ambient dark matter would need some help because this is light dark matter we are probing. So the one such help could come from the cosmic ray scattering, because we are using the hadronic scattering at the end in the detector. So those hadronic scattering or those couplings or these mediators can be utilized also at this cosmic ray upscattering calculation. And then this is the energy of these various dark matter masses and various mediator masses. So this is kind of a 1 MeV mediator, and this is the 100 MeV. So you can see that a lot of flux for various energies, like this is the distribution which we'll be using. But also we will face the neutrinos because, solar neutrinos, atmospheric, geo, and all this stuff. So we have taken all of them into account. And so what we'll do, we'll use the hyper K future, hyper K Dune, and then ongoing Juno and this Borexino, the current Borexino result to put the constraint. And so we'll compare our inelastic constraint with the elastic limit so that you can see how far inelastic constraint can improve upon our searches. And so here, for example, the lines, like here we have the oxygen for the water Cherenkov in the case of hyper K, and then carbon for liquid scintillator in the case of Juno and this Borexino, and argon for Dune. And now combining everything, so this is, I'm hoping that I'm doing fine. Okay, so this is the parameter space. The solid lines here are the inelastic lines. So this V shape comes because of this cosmic ray kind of effect, cosmic ray energy distribution as a function of A prime in this V shape. And then those dark matter would get scattered at the detector. So there again, you find another type of A prime. And so these are all the dotted lines are your elastic constraint. And the current elastic constraint is your LZ. So anything above this within this gray shaded region is already ruled out by the LZ constraint. And so this green one is the Juno, and 200 kilotons, so 20 kiloton for 10 year. And then also we have the hyper K, and then then Dune, and then Borexino. And so Juno is doing much better because the strength of this carbon is higher, much better than the argon. And so now one can also compare these limits with the beam dump based limit. But beam dump, we made an approximation that the A prime has to be bigger than the 3 times bigger than the M chi. So, but here for the ambient dark matter, of course, there is no such like a approximation. But if you compare this with the in the beam dump plane, of course, beam dump would do much better because higher intensity. But again, you use some like a relationship there. But if you use it for any MCHI, if there is no relation, then this direct detection experiment gives you a much better constraint. Also, the inelastic seems to be much better than the elastic, just because we are looking for a line signal and the different kinds of neutrino background you are facing there. So now I would conclude by, like a like a sub-GeV scale could be very interesting for proving or kind of describing new physics scenarios like a dark matter or the neutrino, origin of neutrino masses and mixing, and then various anomalies. And here we then use that sub-GeV dark matter and these nuclear de-excitation lines to show the sensitivity. Actually, these nuclear de-excitation lines could be interesting for other purposes. Like for example, this maybe there could be a way to probe atomic anomaly in a different setup, or producing these A primes and or these scalars in some other ways, or light mediators in some other ways, or producing signals in some new ways in various detectors. Yeah. Thank you.
Thank you, Professor Dutta, for a really great talk. So we are now open to questions, and participants can raise hands if they want to ask a question, or post their question in the chat. Okay, I see Susan.
Yes. Hi.
Hi, Susan.
Thank you for your talk. I actually have a separate question. In regards, since the coherent experiments just down the road from us at Oak Ridge, went through these things, and I understood that. I was wondering if you could comment on the ability to on the possibility of non-standard neutrino interactions, and in particular, there seems to be some kind of, and this is not your talk, and I apologize, but I thought you'd be quite expert. And this is this issue of whether or not there would be non-trivial, non-standard neutrino interactions that emit a different large mixing angle solution for the neutrino mixing problem versus just ordinary neutrino mixing angles. And the coherent experiment apparently can possibly give insight on this.
Yes.
Maybe
Actually,
you could comment on this intriguing possibility also.
Yeah. So, for example, like for NSIs, we analyzed coherent data, and in fact, the interesting piece of coherent or this type of experiments is that you can use the both timing and energy distribution. And what does timing and energy distribution do for you? They can give you the flavor decomposition, because prompt is basically nu mu, and then your delayed comes from nu mu bar and nu e. And now if you look at this in a spectra, and then you can kind of get a flavor decomposition. And in fact, recently we utilize this flavor decomposition in the context of a EV scale sterile, and show that it can, or it has already started to cover the best parameter space. So in their future run, they would do that, like because now you can look for nu e disappearance, because these experiments would look for the disappearance, because that's the way their signal would be. Also, you can see the nu mu disappearance, and combining these two, of course, you can start probing the mini Boone Lessendia anomaly, but that's a different thing. But what you said, that using this flavor decomposition, one can really probe the NSIs for for any of these flavors in a kind of a very interesting way. And we have done some work, but we are doing some more additions to that by adding these light mediators. We have done work on these heavy mediators, but we are now doing some light mediators. And with the heavy mediators, we found that coherent can provide a very interesting constraint. Probably in some regions, it has the best possible constraint because of this flavor decomposition.
Thank you very much.
Mm-hmm.
Okay, Baha.
Hi, Bhaskar. Thanks for a very nice talk.
Wow,
Following up on what Susan was asking, how well can one distinguish, say, heavy mediators of new neutrino forces from sterile neutrinos in coherent experiment? I mean, do you probably have looked at it and
yeah. So again, the for the sterile scenario, so heavy mediator gives you a modification. This is basically a disappearing
right.
experiments, right? And now the way you can either make them disappear by oscillation or introduce some additional cross section. So you can see that there is a degeneracy there. So either or. So now, for example, when we use that the coherent result to probe based, we assume that there is no NSI. Of course, if I bring in NSI, it would be mass. So I buy that. So there is a, you use timing and energy to distinguish flavors, but within flavor, if you have the oscillation versus this like a cross section, that one is a tricky one. So that one cannot be.
Yeah, thank you.
Okay, any more questions? Actually, I have one question. So, when you showed the bound in your model for like different neutrino experiments, and you mentioned like Juno does better. Is it mainly because like size? Is there a size dependence of the neutrino detector, or is it because the background is more constraining there? What goes
Okay,
it?
so good question. So you wonder what, and actually, if you have noticed that plot, there is another interesting piece. So let me. Okay, sorry. So see, the Borexino is also very close to Dune, liquid argon. So Borexino is not is smaller than the Dune size. So its the size is not does not matter there, but the most interesting piece is the carbon versus argon. Carbon for the 15 MeV, if you calculate the cross section, the strength, the GT transition strength is much higher. So that's the reason. And actually, that's why, in fact, when we first started looking for this nuclear inelastic effect, then just going back, and we first calculated it for coherent, and then cis is, which is argon. And then we realized, we thought that we need something with carbon, because by then we realized that carbon gives you the maximum strength. And then we found that indeed, Carmen not only used the data, we did not know that what Carmen used, but we were looking for something with carbon, and then we found that Carmen is using liquid scintillator. Not only that, they also found the peak. And then we figured out they found the peak just because it's a CH2, like a liquid scintillator. And similar detector size, a little bit more POT than CCM, but they see the peak because, or the de-excitation line, just because they used carbon. So it's if you use a carbon detector, so you now need to choose your detector in such a way so that your that GT, lowest GT transition, that strength is larger.
Thank you. Let's see. Any more questions for the speaker? Okay, I don't see any more questions. So thanks again, Professor Dutta, for excellent talk and discussion.
Thank you.
Thank you.
Thank you. Thank you, Baha.
Thank you.
Thank you very much.